Okay, let's talk about sound waves here. So remember, sound waves are longitudinal waves. So the particles move in the same direction that energy is being transferred in. So say we got this speaker here emitting, let's say for example, just one single note. So it's bouncing back and forth and it's moving air particles back and forth, back and forth. Remember that waves transfer energy, not particles. So air molecules are not moving down a line here. Air particles are moving back and forth. So here we're measuring how far an individual air particle has moved from where it was before the sound started. And we could measure that if this source were just emitting a single tone, then that might be like a sinusoidal, a cosine type wave. Particles moving maybe starts here, moves in, moves back, moves over to the other side, moves back, just goes back and forth like this. So that leads to high pressure zones. When particles from, say, both sides come together, we get these high pressure zones and these low pressure zones. And we call these compression zones and rarefaction zones. So what's actually moving left and right here, what's being transferred are not air particles, they're just bouncing back and forth. Energy is being transferred in the form of a wave. Now, not all sound waves are nice sinusoidal, pretty waves like this. If our speaker were emitting an A note, our sound wave would look like this. If it were emitting just noise, it wouldn't be this pretty. But these are waves. So we might have, say, a tuning fork. The sound waves would be traveling out in all directions spherically away from that tuning fork, and we'd have these high pressure zones followed by low pressure zones and so forth. And this is moving. So this high pressure zone would be moving and low pressure zones following behind and so forth. And recall, our wave speed, the speed at which the wavefront moves, the speed at which this high pressure zone is moving, is v, and v equals lambda f. Lambda is our wavelength. That would be the distance from one high pressure to the next, or the distance from one low pressure to the next. Frequency is how fast this thing is vibrating in hertz, cycles per second. So if this thing were vibrating at 440 times per second, that would be an A note. And V is our wave speed, lambda is our wavelength. Okay, so what determines V? So we've got our tuning fork, it's emitting a certain frequency. That we determine through the physical properties of the tuning fork. We build a tuning fork to have a pitch of an A note. What's going to determine lambda and V then? Well, that's going to depend on the properties of our medium that our sound wave is traveling through. So just like we had back when we were talking about waves, our wave speed is the square root of some elastic property of our medium divided by some inertial property of our medium. So before, with regular waves, like waves on a string, we had square root of F over mu. So F was the tension in our string, and mu was our mass per unit length. In general, if we generalize that to any kind of sound wave or wave traveling through a medium, we have three different things we could have: some kind of volume of a solid, a liquid, or a gas. So we have all these different formulae. We're not really going to do anything with these this semester. I'm just showing you that they do exist. Here's the formula we would use to calculate the wave speed through a gas. And notice that that has R that you learned in chemistry, the ideal gas constant. Okay, so here are some examples of wave speeds through certain media. These are all at 0 degrees Celsius. So air is about 331. That's at 0 degrees Celsius, which is, the freezing point of water. That's pretty cold. Wave speed, the speed of sound in air depends on temperature and density of the air, the humidity of the air, depends on a few factors. So we'll be using numbers kind of close to this depending on the application. So 334 you're going to see pop up quite a bit. Just depends on our temperature, our humidity, our altitude, because that will help determine the density of the air and so forth. Now you can see here, waves travel a lot faster through water than they do through air. The denser the medium, the faster the wave speed. Okay, and we can see here, this is wave speed, speed of sound in air, depending on temperature, where T here is in Kelvin. So here's a generalized formula we could use in pretty much every application. They're just going to tell us what speed of sound to use for that particular application. And you'll see 334 meters per second comes up quite a bit. Okay, something else we're interested in when we're talking about sound is how much energy is being transferred by that sound wave. So recall from when we were talking about waves, we talked about intensity. The intensity at some point away from a sound wave is the power that's being emitted divided by the cross-sectional area of an expanding sphere around your source. So if we look here at this tuning fork, these sound waves are traveling out, and if I'm out some distance r away, that sound wave is really a big sphere of radius r. Well, all that energy that this thing was emitting is now being spread out. So the intensity out here is much lower than it is in here, closer in. Because the power is constant. Power is watts per second, or power is watts, joules per second, energy per unit time. This thing is emitting sound at a constant power, a constant energy rate. That energy is being spread out over bigger and bigger surface areas, so the intensity is decreasing. So at a certain distance, our intensity, which is measured in watts per square meter, will be the power at the source divided by the surface area of a sphere at that distance. So if we want to compare two intensities at different radii, the power will be the same, we'll just have different radii. So if I go out double the distance, if R2 is twice R1, then this fraction in here would be a half. 1/2 squared would be 1/4. We would get 1/4 the intensity. Okay, so we have intensity, which is how much energy is flowing per unit time through some area. That's measured in watts per square meter. We like to measure that on a logarithmic scale that we call the decibel scale. So you're going to get these two terms confused. Sound intensity is I. Sound intensity level is decibels. We call that beta, and that's our decibel scale. And this is a measure of loudness. But it is a logarithmic scale. So our decibel level at some point in space is 10 times log base 10, the common log, of the intensity at that spot divided by this thing we call I naught. I naught is about the threshold of human hearing. It's about the lowest sound that we can hear. And it's 1 times 10 to the negative 12th watts per square meter. Everything on the decibel scale is measured in relation to that. How many times bigger are we than that number? So we've got it here in our formula. Okay, so here are some decibel levels for some, common examples. So an average home has a sound intensity level of about 40 decibels. The average office is about 50 decibels. Now remember, you always have to remember that the decibel scale is a logarithmic scale. So an increase of 10 decibels means you're 10 times louder. The average office is 10 times louder than the average home because we went up by 10 decibels. If you go up by 20 decibels, it's 100 times louder. So you might think 100 decibels, that's a factory. A loud rock concert's 120 decibels. That's not that different. 100 and 120, that is very different. That's 20 decibels bigger. That means it's 100 times louder, 100 times more intense, 100 times the energy per second per square meter is being emitted. And I've got extra videos just on decibel scale. This is just a rough overview.